sun looks permanent because every human life has been lived under its regular light. It rises with the same authority over deserts, oceans, cities, forests, wars, harvests, ruins, and childhood mornings. It has watched entire civilizations mistake repetition for eternity. In the ancient world, it was a god. In modern physics, it is a sphere of plasma held together by gravity, burning hydrogen in its core with a patience so vast that our history barely registers against it. Yet the same laws that make the sun shine also condemn it to change. The death of the sun will arrive without violence by stellar standards. There will be no supernova, no instant detonation tearing the solar system apart, no single day when the sky splits open and the star ends in one blinding catastrophe. The sun lacks the mass for that kind of death. Its ending will be slower, stranger, and in some ways more intimate. It will age from within, alter the balance of worlds around it, erase the conditions that made Earth gentle, and eventually abandon the form by which every eye on this planet has known it. To understand that ending, we must begin with the uncomfortable fact that the sun is already changing. Every second, it turns hydrogen into helium and loses a little mass as light. Every second, the balance inside its core shifts by an amount too small for us to feel, yet decisive over deep time. The future disaster is already being prepared in the present warmth. The noon sunlight on a window, the shimmer on a sea, the gold on a field of wheat all come from a process that cannot continue forever. The sun survives through a bargain between two forces. Gravity tries to pull everything inward, drawing the whole star toward collapse. Fusion pushes outward, filling the core with pressure born from heat, radiation, and the transformation of matter into energy. For now, those forces hold each other in balance. The result is the steady yellow light of an ordinary G-type star, a star neither enormous nor tiny, neither short-lived nor nearly eternal. It is modest on the scale of the galaxy, yet it is the single condition behind almost everything that has ever happened on Earth. At the center of the sun, hydrogen nuclei are pressed so tightly and heated so fiercely that they merge into helium. This fusion process releases energy, and that energy begins an immense journey outward. A photon born in the core may scatter through the solar interior for thousands of years before it reaches the surface. When it finally escapes into space, it crosses the distance to Earth in just over 8 minutes. By the time it touches skin, leaf, ocean, ice, or stone, it carries the ancient pressure of the solar core into the fragile present of a living planet. This balance gives the sun its apparent serenity. The surface boils with granules larger than countries, magnetic fields twist and snap, flares burst into space, and storms of charged particles race outward through the solar system. Still, from Earth, the sun appears reliable. Its turbulence is hidden beneath habit. We have built calendars, agriculture, architecture, mythology, and science around its consistency. The deep truth is less comforting. Stability in a star is never stillness. It is a controlled fall, a continuous correction, a long negotiation between collapse and fire. The fuel that makes this negotiation possible is finite. The sun began its life with a vast supply of hydrogen, but the hydrogen in its core is being consumed. The outer layers still contain abundant hydrogen, yet the core is the furnace where fusion can occur under the required pressure and temperature. Over billions of years, helium accumulates where hydrogen once dominated. The core slowly changes its composition, its density, and its behavior. The sun remains bright because it adapts, and those adaptations become the first steps toward its death. As helium builds up in the core, fusion has to proceed under slightly different conditions. The core contracts, grows hotter, and causes the outer layers to shine more strongly. This has been happening through the entire history of Earth. The young sun was fainter than the sun we know today. The future sun will be brighter still. The difference is subtle over a human lifetime, but over hundreds of millions of years it becomes a planetary force. The end of the sun begins long before the star leaves the main sequence. It begins as an almost imperceptible increase in light. Earth will suffer the consequences of the sun's aging long before the sun itself looks old. The first great transformation will come through brightness, not expansion. As the solar core continues to evolve, the sun's luminosity will increase gradually. A slightly brighter sun may sound gentle, almost benign, but climate systems are built on thresholds. A world can absorb small changes for a long time, then cross a boundary beyond which familiar balances fail. Earth's oceans, clouds, rocks, atmosphere, and living systems are tied together with delicate exchanges of heat and chemistry. At first, the future warming will be measured in changes too slow for any generation to recognize as a disaster. Weathering of rocks will draw carbon dioxide out of the atmosphere. Plants will struggle as carbon dioxide declines. Ecosystems will change in ways that would seem apocalyptic to the creatures living through them, yet quiet from the perspective of astronomy. Forests will shrink, deserts will spread, and the web of life will lose some of the chemical foundations that made complex ecosystems possible. The first end of Earth may come under a blue sky. Then the oceans begin to matter in a darker way. Water is a protector, a climate regulator, a solvent for biology, and a reservoir of memory. It is also a greenhouse gas when carried into the atmosphere as vapor. As the sun grows brighter, more water evaporates. More vapor traps more heat. More heat releases more vapor. A feedback begins to tighten. The planet that once used its oceans to moderate warmth will find those same oceans helping to intensify it. The seas will still glitter for a time, but their beauty will belong to a system moving away from life. In the far future, Earth may enter a moist greenhouse state. Water vapor reaches higher into the atmosphere, where sunlight can break molecules apart. Hydrogen escapes into space. Oxygen reacts with rocks and minerals. The ocean slowly loses itself upward, not as a flood, not as a dramatic boiling in one cinematic afternoon, but as a planetary dissociation across immense time. The future death of Earth's oceans is among the most haunting parts of solar evolution because it turns the most familiar image of life into a process of disappearance. Human beings often imagine the end of Earth as a collision, an impact, a war, or a sudden cosmic accident. The sun offers a slower verdict. The same star that allowed liquid water to persist will eventually withdraw that permission. Habitability is a temporary arrangement between a planet and its star. Earth's position in the habitable zone is not a permanent address. It is a passing interval in the life of the solar system, and the interval is already moving. The loss of the oceans would transform Earth beyond recognition. Coastlines, once among the most fertile and crowded edges of civilization, would become scars around empty basins. Continental shelves would dry into immense terraces. The abyssal plains, hidden through all human history under black water, would lie exposed to a punishing sky. Mountain chains beneath the sea would become ridges across dead salt deserts. Places no eye had ever seen without machines would become part of a global wasteland. The atmosphere would thicken with heat and vapor before it thinned through loss. The familiar blue of Earth from space would change as clouds reorganized and seas vanished. A planet once known for reflection, weather, and living color would grow stark. Its climate would become less like the world of rain and seasons and more like a furnace with geography. The continents would still remember rivers in their channels, but no river would remain to follow them. Ancient deltas would point toward seas that had become minerals. Life, if it survived into those epochs, would retreat into refuges. The largest organisms would vanish first. Complex animals require stable ecosystems, oxygen cycles, food webs, and water in forms that do not punish every cell. Plants would decline as carbon dioxide became scarce and heat intensified. Microbial life might persist far longer in underground pockets, deep crustal water, salt deposits, or protected chemical niches. Earth's final biosphere may be invisible from the surface, surviving in darkness while the sun grows too bright above it. This future gives the death of the sun a tragic inversion. The star will still appear luminous and alive while Earth becomes hostile. The catastrophe arrives while the sun is still on the main sequence, still recognizably itself, still performing the same basic fusion that has powered it for billions of years. The visible sun will not yet be monstrous. It will simply be too generous with light. A small increase in output, sustained for long enough, becomes an executioner of oceans. By the time the sun visibly swells into a red giant, Earth's age of life will almost certainly be ancient history. The planet may already be sterile on the surface, its oceans gone, its rocks altered, its atmosphere transformed. This is one of the most important truths of the sun's death. The drama we would notice in the sky comes after the deeper loss has already occurred. The disappearance of habitability precedes the spectacle. The end of Earth as a living world happens before the sun becomes visibly old. For billions of years, the sun's core has been converting hydrogen into helium. This is the main sequence, the long adulthood of a star like ours. It is the period of relative stability, the era in which planets can settle, atmospheres can evolve, chemistry can become biology, and biology can become memory. The sun has spent most of its life in this state. It will remain there for billions of years more. Yet the direction is fixed. The core is becoming less hydrogen-rich and more helium-dense with every passing moment. When the core hydrogen becomes too depleted to sustain the same kind of central fusion, the sun will undergo a major internal rearrangement. Fusion will continue in a shell around the inert helium core. The core itself will contract under gravity, becoming hotter and denser. The outer layers will respond by expanding. This is the beginning of the red giant phase, one of the most profound transformations in the life of a sun-like star. The star that once held its radius with relative modesty will begin to occupy a far larger volume of space. The change is slow compared with explosions, yet enormous in consequence. The sun will brighten dramatically. Its surface will cool in temperature compared with its present photosphere, which shifts its color toward redder light. But its total energy output will rise because the surface area becomes vast. The star will become bloated, luminous, and unstable. Its outer atmosphere will reach outward through the inner solar system. The familiar scale of planetary orbits will begin to feel fragile against the body of the aging star. Mercury will be doomed. Venus will be doomed. Earth's fate is more complex in calculation because the sun will lose mass as it ages, and planetary orbits can expand outward as the central gravitational pull weakens. Yet tidal interactions, drag from the expanded solar envelope, and the sheer violence of the red giant phase may still draw Earth into destruction. Even if Earth avoids direct engulfment, survival would be only orbital. The planet would be a scorched remnant circling a dying star, stripped of the conditions that once made it meaningful to life. The red giant sun would dominate the sky beyond anything human imagination associates with sunrise. If any observer could stand on a surviving world or moon in the outer solar system, the sun would appear enormous, red, and oppressive, pouring out far more energy than today. The cold regions of the solar system would change. Icy moons might thaw for a time. Frozen landscapes that had spent billions of years in darkness could briefly enter a strange, late warmth. The death of the sun may bring a temporary spring to worlds that never knew one. The red giant phase will turn the inner solar system into a region of ruin. Mercury, so close to the sun even now, will have little future once the sun expands. Venus, already a world of suffocating heat, will be overtaken by conditions far beyond its present hell. Earth, once the blue center of human concern, will face either engulfment or extreme roasting under a swollen star. The rocky planets that define the inner architecture of the solar system will cease to resemble worlds in any familiar sense. If Earth remains outside the solar envelope for part of this transformation, its surface will be molten or close to it. The crust may soften, collapse, and reform under intolerable heat. Minerals will change. Ancient continents may lose their shape. The last traces of oceans, sediments, fossils, cities, and biological history would be either destroyed or buried inside a geology made incandescent. Every archive made by life depends on a planet cool enough to keep form. When that condition fails, memory becomes mineral noise. There is a particular cruelty in the thought that Earth might physically survive after becoming unrecognizable. A dead planet can continue to orbit. A world can persist after its meaning has been burned away. The Earth of that era would carry the mass of its old self, perhaps even the broad outline of its orbit, yet none of the tenderness attached to the word home. It would be a remnant under red light, an object in dynamics, a former biosphere reduced to rock. Farther out, the transformation would be more ambiguous. Mars, the asteroid belt, the moons of Jupiter and Saturn, and the distant icy bodies beyond Neptune would all receive more sunlight. Regions now locked in cold could warm. Subsurface oceans may respond. Ices could vaporize. Atmospheres could form temporarily. And chemistry could become active in places that were frozen through the sun's main sequence life. The red giant sun will destroy the old habitable zone and push warmth outward, turning the solar system into a different kind of experiment. This late warmth should not be imagined as a new Eden. The red giant phase is unstable, intense, and temporary. Any thawing of outer moons would occur under a star losing mass, swelling, pulsing, and shedding material. It would be a twilight ecology at best, if life or chemistry were present at all. The solar system would experience a final redistribution of light, a last disordering of the old arrangement, before the sun gives up its outer layers and begins its retreat into a remnant. The sun will not die as a supernova. That fact matters because it defines the emotional shape of its ending. Massive stars live briefly and die violently, forging heavy elements in their interiors and scattering material through space in catastrophic explosions. The sun belongs to a quieter class. Its mass is too low to collapse into the kind of core that produces a supernova. It will age, swell, shed, and contract. Its death is a long unbinding. This does not make the process gentle. A red giant can devastate its planetary system without exploding. Its outer layers can expand across hundreds of millions of kilometers. Its luminosity can rise by orders of magnitude. Its winds can strip material into space. Its gravity, changing as mass is lost, can rearrange orbits and destabilize smaller bodies. The solar system will not experience a single detonation, but it will endure a prolonged upheaval in which the central star ceases to behave like the stable anchor it once was. As the sun climbs the red giant branch, helium in the core will eventually reach conditions hot enough for fusion. Helium nuclei can combine to form carbon and oxygen. For a star like the sun, this stage arrives after the core has contracted and heated under tremendous pressure. The ignition of helium changes the internal structure again, briefly giving the star a new source of energy. Yet this is not a return to youth. Helium fusion is a later chapter, shorter and more fragile than the long hydrogen-burning era that preceded it. After helium burning becomes established, the sun will enter another phase of complexity. It will build a core rich in carbon and oxygen, surrounded by shells where fusion continues in layers. The outer envelope will become unstable. Pulsations may grow stronger. Mass loss will increase. The sun will begin to cast off the material that once made up its visible body. What had seemed like a single, indivisible star will reveal itself as a structure capable of shedding its own atmosphere into interstellar space. The phrase, "death of the sun," can be misleading if it suggests a moment. Stellar death for a sun-like star is a sequence. The sun will pass from stable fusion to shell burning, to red giant expansion, to helium burning, to renewed instability, to the loss of its outer layers, to a bare remnant. Each stage follows from gravity, pressure, nuclear physics, and time. There is no intention in it, no punishment, no cosmic theater arranged for human fear. That is precisely why it is so powerful. It will happen because matter behaves this way. When the sun reaches the end of its red giant and later giant phases, it will begin to lose its outer layers into space. These layers will drift away as expanding gas, illuminated for a time by the hot core left behind. Astronomers call such structures planetary nebula, a historical name from an era when early telescopes made some of these glowing shells look like planets. They are not planets. They are the exhaled atmospheres of dying stars, brief luminous sculptures made from the remains of stellar envelopes. For the Sun, this phase may be one of the most beautiful and least humanly survivable events in its history. The star's outer material, enriched by the products of nuclear processing, will move outward into the surrounding darkness. Gas will glow under ultraviolet radiation from the exposed core. The solar system's central light will become strange, sharp, and spectral. The familiar Sun, the disk that once rose through haze and set behind mountains, will have become a hot remnant surrounded by its own departing skin. Planetary nebula structures can take delicate forms: rings, lobes, filaments, arcs, and asymmetries sculpted by winds, magnetic fields, rotation, and possible companions. The Sun may create a faint expanding shell rather than a spectacular nebula visible across great cosmic distances. But the principle remains. A star that spent billions of years holding itself together will finally surrender its outer layers. The material that warmed Earth will return to interstellar space, thinned and scattered, available for future cycles of chemistry. There is a deep continuity in this loss. The atoms in our bodies were made before the Sun existed, in earlier generations of stars and cosmic events. The Sun gathered some of that material into a new system. Earth formed from the same ancient cloud. Life arose from planetary chemistry under solar light. In the far future, the Sun will release part of itself back into space. The death of a star is also a form of redistribution. It is the galaxy reclaiming matter after a long local experiment. Yet this phase will be brief by stellar standards. A planetary nebula glows for only tens of thousands of years before it disperses and fades into the interstellar medium. Compared with the Sun's 10 billion-year lifetime, that final luminous shell is almost a gesture. The most visually poetic stage of the Sun's death may be one of the shortest. The long story belongs to the quiet burning before it and the cooling remnant after it. When the outer layers are gone, the Sun's core will remain as a white dwarf. This object will be roughly Earth-sized, yet it will contain a large fraction of the Sun's former mass compressed into an extraordinary density. A teaspoon of white dwarf material would weigh tons. Its matter is supported by quantum pressure rather than ordinary fusion. The star will no longer shine by making new energy in its core. It will glow with stored heat, radiating away the memory of its former life. The white dwarf Sun will be intensely hot at first, but faint because it is so small. It will sit at the center of a transformed solar system, surrounded by whatever planets, moons, asteroids, comets, and debris survived the giant phases. The old architecture will be damaged. Some worlds may have been swallowed, others scorched, others displaced. The orbits of distant bodies may have expanded as the Sun lost mass. The gravitational center remains, but diminished. The empire of sunlight becomes a compact ember. White dwarfs are among the great clocks of the universe. They cool slowly. Without fusion to replenish their heat, they fade across billions and trillions of years. Their light shifts, weakens, and sinks toward darkness. The future white dwarf Sun will become a relic, a dense cinder of carbon and oxygen, cooling in a universe where the bright age of stars continues elsewhere for a time. Long after Earth is gone as a living world, the remnant of the Sun will still exist, quietly losing heat. Around white dwarfs, astronomers have found signs of planetary debris. Some white dwarfs show heavy elements in their atmospheres, suggesting they have accreted fragments of asteroids, minor planets, or rocky bodies. Others are surrounded by dusty disks. These observations matter because they turn the future of our own system into something we can partially study through other stars. The end of the Sun is distant, but the galaxy contains previews. We see dead suns eating the remains of their planetary systems. That image gives the Sun's future a second darkness. Even after the red giant catastrophe, even after the planetary nebula fades, the white dwarf may continue to disturb and consume fragments from its former system. Asteroids or comets thrown inward by surviving giant planets could be torn apart and scattered into disks. The dead sun may carry traces of its planets in its atmosphere, like chemical memories suspended on a stellar corpse. If some distant civilization studied it, they might infer that rocky worlds once existed there. The outer solar system may outlast the inner planets in recognizable form, though altered by the sun's mass loss and late luminosity. Jupiter and Saturn will almost certainly survive as planets, unless unexpected dynamical interactions intervene over immense timescales. Uranus and Neptune will remain farther out, colder again after the white dwarf stage begins. Their moons, rings, and smaller companions will inhabit a system whose central light has become weak and hard. The old sunlight that once warmed Earth will be reduced to a pale remnant glow. During the red giant phase, some icy moons may experience temporary warming. Europa, Ganymede, Callisto, Titan, Enceladus, and other distant bodies could undergo episodes of surface or atmospheric change if they receive enough energy. The details depend on timing, distance, ice composition, orbital dynamics, and the behavior of the swelling sun. For worlds now known mainly by cold, such a period would be transformative. Frozen surfaces might crack, sublimate, melt, or generate transient atmospheres. A moon that spent billions of years beneath weak sunlight could briefly become geologically restless. Yet the later white dwarf phase would bring a new cold. Once the sun sheds its envelope and shrinks to a small remnant, the outer worlds will no longer receive the same flood of red giant energy. Any temporary atmospheres may freeze or escape. Ices may settle again. The solar system will enter a dim aftermath where survival means persistence, not flourishing. The giant planets may continue to orbit like old sentinels around a shrunken star, carrying their moons through darkness. The small bodies beyond Neptune will also feel the consequences. The Kuiper Belt and distant comet reservoirs respond to changes in gravity over long spans. As the sun loses mass, orbits can expand and become more weakly bound. Passing stars and galactic tides may more easily disturb distant objects. Some may drift away into interstellar space. Others may be sent inward, toward the white dwarf, where tidal forces and radiation can break them apart. The edge of the solar system may slowly leak into the galaxy. In this far future, the solar system becomes less a family of worlds under a living sun and more a fossil structure. Its planets and debris will preserve a record of what once existed, though no record remains safe forever. Gravity continues to work. Encounters occur. Orbits shift. Collisions still happen. A dead star system is not frozen in perfect silence. It is quieter, darker, and colder, but still governed by motion. Even ruin has dynamics. The death of the sun is difficult to feel because it belongs to a scale beyond ordinary fear. 5 billion years is not a waiting period in any human sense. It is longer than the entire history of complex life on Earth, longer than the time since the first oceans, long enough for continents to merge, split, erode, vanish, and rise again. Every language now spoken will be gone. Every city will be dust. Every monument will either disappear or become a mineral trace unless some intelligence deliberately carries memory beyond Earth. Still, the distant future has a strange power over the present. To know that the sun will die is to understand that even the largest constants in human experience are temporary. The horizon, the seasons, the color of daylight, the rhythm of morning and evening, all belong to a cosmic interval. They feel absolute because we are short-lived. Astronomy teaches another grammar. It asks us to place the familiar inside a much longer sentence, one that began before Earth and continues after Earth becomes uninhabitable. There is no practical emergency in the sun's death for us today. The timescales are too large. Our immediate dangers are closer, sharper, and mostly of our own making. Yet the sun's future clarifies something essential. Habitability is rare, local, and temporary. A planet can be perfect for life during one age and impossible in another. A star can be generous for billions of years and lethal by continuing along its natural path. The universe does not need malice to end a world. If humanity or its descendants survive into deep time, they will have to become a species of movement. The future of intelligence cannot rely forever on Earth's orbit. Long before the red giant phase, long before the sun becomes visually monstrous, a technological civilization would need to consider migration, planetary engineering, artificial habitats, or journeys to other stars. The death of the sun turns interstellar travel from fantasy into a distant condition of survival, assuming anyone remains to care about survival on those scales. This does not reduce Earth's importance, it deepens it. A temporary world can still be precious. Perhaps it becomes more precious because its conditions are passing. The fact that Earth will one day lose its oceans does not make the oceans less real today. The future white dwarf does not make the present sunrise meaningless. It places meaning inside time, where all living things have always existed. The sun will die, and for now, it shines. After the red giant storms, after the outer layers drift away, after the planetary nebula fades, after the white dwarf cools through ages longer than human imagination can hold, the sun will continue to dim. It will radiate leftover heat into space with no furnace at its center to renew it. The remnant will pass from brilliant white to yellowish, then redder, then infrared faintness, then near invisibility. The process is so slow that the universe is not old enough for any white dwarf to have cooled completely into a black dwarf. A black dwarf is a theoretical final state. A white dwarf cooled until it emits almost no light. The sun may reach such a state only after immense spans of time, far beyond the present age of the cosmos. By then, the Milky Way itself will have changed through interactions and mergers. Star formation may have declined. The bright stellar age will be moving toward exhaustion. The remnant of our sun would be one cold object among countless others, a dark ember carrying mass without flame. In that final darkness, there would be no memory of sunlight unless memory had somehow escaped its original planet. Earth may be gone, swallowed, shattered, stripped, or preserved only as a dead stone. The moon's fate is tied to the same gravitational history. The inner solar system may be a region of debris and absence. The old days of blue atmosphere and moving water would have no witness unless life had found a way to carry its story outward. The universe keeps objects more easily than meanings. Yet the sun's death is not only an ending in the material sense, it is part of the same cosmic economy that made the sun possible. Gas clouds collapse, stars ignite, planets form, worlds cool, chemistry searches through its possibilities. Life may arise, look back at the star that feeds it, and eventually understand that the gift has a limit. The sun's future death is written into the physics that gave Earth a beginning. Creation and loss share the same equations. The most honest image of the sun's death may not be the red giant filling the sky, or the white dwarf in darkness, or the dry basins of vanished oceans. It may be the present sun seen with full knowledge of its impermanence. The ordinary disk above us is a star in the middle of its life, still stable, still luminous, still capable of warming a living world. Its death is far away, but its mortality is already true. Each sunrise is part of a finite sequence. One day there will be a last sunrise on Earth, though no human eye may see it. One day there will be a last ocean under the sun, a last cloud made from terrestrial water, a last living cell warmed by the star that made all later history possible. Long after that, the sun will swell, shed, shrink, and cool. The star that filled our sky will become a relic. The center of our days will become an object of night. And somewhere in the record of the universe, for a brief and astonishing interval, a small blue planet turned sunlight into forests, weather, thought, and songs. The most unsettling part of solar death is that its earliest signs are indistinguishable from normality. The sun does not need to flicker, redden, or swell in the sky for the future to begin. Its core already contains the mechanism of change. Helium ash accumulates at the center, fusion adjusts around it, and the star slowly brightens as a consequence of its own maturity. To a human observer, the difference between one century and the next is lost beneath weather, climate, dust, volcanoes, and the variations of Earth itself. To a planet, given enough time, that difference becomes destiny. This slow brightening also reveals why the habitable zone is a moving boundary. It is often imagined as a ring around a star, a region where liquid water can exist on a rocky planet. In reality, it is a historical condition. It shifts as the star evolves, as atmospheres change, as planetary surfaces weather, as clouds respond, as oceans absorb and release heat. Earth lives within that zone now because many conditions happen to overlap. In the future, the zone moves outward. Earth remains in its orbit, faithful to its old distance, while the terms of habitability drift away from it. There is a quiet violence in a boundary moving too slowly to be seen. No creature can feel the habitable zone leaving. No forest can understand that the chemistry of its air is becoming part of a stellar problem. No ocean can know that its vapor will one day help lift its own hydrogen into space. Yet the system changes. Small adjustments accumulate. The future Earth becomes less forgiving long before it becomes visually alien. A world can lose its future while still resembling itself. For viewers of deep time, this is the first moral shock of the sun's death. We are used to associating danger with disturbance, an impact, an eruption, a flare, a sudden darkness. Solar evolution teaches a different kind of danger, the danger of continuity. The sun keeps shining. It follows its nature. It remains faithful to the physics that sustained life, and through that same faithfulness, it eventually removes the stage on which life appeared. The tragedy has no villain. It has only duration. When the sun becomes a red giant, the geography of warmth will move outward through the solar system. Places that now exist at the edge of sunlight may enter a strange late afternoon. The moons of Jupiter and Saturn, long frozen at the surface, may receive enough energy to transform their outer layers. Ices could soften or sublimate. Dark plains could brighten with vapor. Crusts that had stored fractures for billions of years could open under thermal stress. The outer solar system may briefly become more active, just as the inner worlds become ruins. Titan is one of the most evocative examples. Today, it is a cold moon with a thick nitrogen atmosphere, methane lakes, organic chemistry, and a surface shaped by processes that resemble weather in alien form. Under a brighter, older sun, Titan could change dramatically. Methane cycles might collapse or intensify depending on the energy received and the duration of warming. Water ice, now as hard as rock, may behave differently. The moon could become a laboratory of transitional chemistry, warmed too late and under a star too unstable to offer a long calm. Europa and Enceladus suggest another possibility. Both are associated with subsurface oceans beneath ice, maintained by tidal heating rather than solar warmth alone. A red giant sun might alter their surfaces while their interiors continue to be shaped by gravity and heat from within. If any form of life ever existed in such hidden oceans, the red giant phase would not necessarily make those habitats simple or safe. It could change ice thickness, chemistry, radiation exposure, and surface exchange. A temporary increase in sunlight can disturb as much as it can liberate. This outward migration of warmth gives the sun's death a strange asymmetry. The worlds that knew daylight best will be destroyed by too much of it. The worlds that spent the longest time in cold may receive a final interval of transformation. It is possible to imagine, in a purely speculative sense, a future civilization or descendant intelligence using the outer solar system as a refuge while Earth becomes impossible. Such a future would be difficult, temporary, and dependent on technologies far beyond ours, but it shows how stellar death rearranges value. The center becomes dangerous. The margins become meaningful. Still, the red giant phase offers no stable sanctuary. It is a storm of time. The sun's luminosity changes, its radius changes, its winds intensify, and its mass decreases. Orbits respond, atmospheres escape, surfaces erode or freeze again when the white dwarf phase begins. Any warmth in the outer solar system would be a borrowed season near the end of the star's life. It might last long enough to matter to geology, chemistry, or survival strategies, but it would remain a passage. The sun's final generosity would be unstable by nature. We know the sun's fate because the galaxy is filled with older examples. White dwarfs are not abstractions in equations. They are observed objects, cataloged by telescopes, measured through their light, mass, temperature, spectra, and motion. Many are the remnants of stars that began their lives broadly like the sun, then passed through red giant expansion, envelope loss, and contraction into dense cores. When astronomers study white dwarfs, they are looking at the future in distributed form, scattered across the Milky Way. Some white dwarfs reveal the remains of planetary systems around them. Heavy elements appear in their atmospheres even though, under strong gravity, such elements should sink out of sight relatively quickly. The likely explanation is ongoing accretion. Fragments of rocky bodies, asteroids, minor planets, or icy worlds falling onto the dead star. Dusty disks around certain white dwarfs strengthen that picture. The remnant star becomes a forensic site. Its atmosphere holds chemical traces of worlds that formed, survived for a time, were disturbed, shattered, and consumed. These systems give our solar system's future a scientific texture. The sun's death is not simply an extrapolation from theory. It belongs to a pattern seen elsewhere. We observe stars that have already become white dwarfs. We observe debris around them. We observe signs that planetary systems can persist after stellar death, though in damaged and rearranged forms. The planets do not always vanish in the red giant phase. Some survive, some migrate, some are thrown into new paths, and some eventually fall inward as fragments. Survival and destruction can occupy the same system. This is why the white dwarf sun may become chemically haunted. If asteroids or planetary fragments fall inward after the giant phases, their material could pollute the white dwarf atmosphere. A distant astronomer might detect calcium, iron, magnesium, oxygen, or other elements, and infer the existence of rocky bodies in the system's past. Perhaps Earth itself would leave no direct trace. Perhaps the moon, asteroids, or fragments of inner planets would provide the clues. A dead system can still testify, though the testimony is partial. There is something moving about this scientific afterlife. The sun, which once allowed life to read the universe, may one day be read by another intelligence as evidence. Its remnant light, faint and compact, could carry information about lost planets. The ruins around it could suggest that matter once gathered there into worlds. No telescope could recover the sound of rain, the green of forests, or the lives that unfolded under ordinary sunlight. Yet chemistry might preserve a colder message. Rocky planets existed here. A star died here. Something complex may have happened before the dark. The death of the sun is distant enough to be useless as an immediate fear, yet profound enough to change the way the present is understood. It tells us that stability is a phase, not a possession. The solar system is not a finished architecture. It is a temporary arrangement of masses, energies, temperatures, and orbits. The sun is not a lamp fixed above creation. It is an evolving star, and Earth is living through the mild middle of its story. We occupy the interval when the light is strong enough for oceans and gentle enough for cells. This interval has already lasted a very long time. Earth formed more than 4 billion years ago. Life appeared early in planetary history. Complex organisms took much longer. Human civilization arrived at the very end of that chain during a narrow climatic and astronomical moment. We look backward and see deep time as a climb toward consciousness. But the sun reminds us that the climb does not continue on the same stage forever. The theater itself changes. The star grows older. The world that made observers possible will eventually become unable to host them. There is humility in this knowledge. It removes the illusion that the cosmos was arranged to preserve us indefinitely. It also gives the present an austere beauty. We live under a star stable enough to permit memory, language, grief, science, and art. We can calculate the future death of the very sun that allows us to perform the calculation. A living planet has produced minds capable of seeing past the lifespan of the living planet. That fact is almost impossible to hold without wonder. The story of the sun's death therefore becomes more than an astrophysical sequence. It is a scale against which human urgency and human tenderness can be measured. Our lives are brief, yet they occur during a rare epoch of warmth and visibility. Our conflicts are loud, yet they unfold beneath a star that will outlast every empire and eventually outgrow every shoreline. Our achievements may vanish, yet the act of understanding where we stand gives them a different kind of dignity. Knowledge does not make the ending disappear. It allows the ending to be seen clearly. When the sun finally becomes a white dwarf, the age of Earth as a cradle will be over. When the white dwarf cools into deeper darkness, the memory of sunlight will depend on whatever life managed to preserve beyond its origin. Perhaps nothing will remain. Perhaps intelligence will scatter among other stars. Perhaps machines, descendants, archives, or forms of life we cannot imagine will carry the old story outward. The physics is clearer than the future of meaning. Matter follows laws. Memory requires caretakers. For now, the sun is still in its long middle age. It rises over water. It feeds leaves. It powers storms, seasons, wind, climate, and sight. It burns 4 million tons of mass into energy every second, and from that loss comes the world we know. The death of the sun begins inside that generosity. Its ending is already encoded in its light. To look at the sun, safely, indirectly, through atmosphere, reflection, or shadow, is to see both a beginning and a limit. The star that made our days is mortal, and every day beneath it is part of the finite grace before the fire changes form.